Good afternoon. Welcome back to the last ECE 442-542 lecture for spring 14. You don't all have to be celebrating quite so dramatically, but teacher course evaluations are still open for the next few hours. The number has, or the percentage of respondents has improved since the last time. It's gone up 10%. It's now over 60%. I want to see if I can get that up even higher, but I can't prod specific people because I don't know who has and who has not. But I appreciate those that have, and if you haven't yet, please take a few minutes before you go to bed tonight or before you start studying. Anyway, do it before 11:59 tonight or it will be closed. We will have a final exam review session, so that will cut into your time interval that you have to respond to the teacher course evaluation if you stay for that review session, and that's going to happen here at 7. The office hours for the remainder of the week are modified from the typical office hours. Tomorrow I won't have any morning office hours. That's the Thursday of reading day. The office hours are slid to 2 o'clock to 4 o'clock on Thursday, and just to be consistent, they'll be the same time on Friday. Hopefully you don't have too many really dramatic questions at 4 o'clock, which is 2 hours before the final exam. And as a reminder, there is an extra credit opportunity if you want to do homework number 8, and I would suggest you do work homework number 8 because problems on the final exam will be coming from homework 8. Maybe not all of the problems on the final exam, but some of them. As I said, the final is 2 days from now, and it's a little bit more than 48 hours, but not much. So set your alarm for sometime 48 hours from now, and that will get you here on time for that exam. And make sure that you've done whatever you need to do to stay alert and on top of your game for those 2 hours from 6 p.m. to 8 p.m. on Friday. Tonight's goals, or this afternoon's goal, depending on, or this morning's goal, depending on how your day has started. Final exam info, I'll just quickly scroll through that. Maybe we'll talk more about that in the review session, but at least you'll have it in 2 locations if you want to refer back to that. Today, a picture is worth how many words? 5? I know this is a discrete class, but 5 is a little low. Don't they say 1,000? Picture is worth 1,000 words. I'm going to give you many thousands of words in the first part of the lecture. All of these blue dots are going to be pictures. I want to play on your visual conception of what we're talking about when we talk about state space design. We'll look at state space design first by just reminding ourselves what the state space representation looks like as a block diagram. And then we'll start building on top of that. So if you like to build things, if you're a hands-on person, now is the chance to draw those builds in the state space design approach. We'll look at state space feedback. We'll look at full state feedback with non-zero reference input. That's all on homework 8. Then we will move into integral control, which connects this PID control concept, or at least the integral part of the PID, to state space design approaches. And why do we like integral control? Just as a question for your final conceptual understanding, what's so good, or why do we like integral control? Or do we like integral control? It helps us with our steady state error or our steady state accuracy. But it does possibly have to be traded off with transient performance, because it now puts another pole right on the stability boundary, and that may negatively impact our transient performance. So we always have to keep that in mind when we're dealing with integral control. All of those topics have assumed that we have access to every one of the state variables in our state vector. If we had 10 components in our state vector, then we're assuming we can measure all 10 of those. Maybe it's 2 positions, a couple of voltages, some currents, some temperatures. All of those are, let's say, state variable components. We're assuming we have access to those in this state variable design approach until the last 2. Now we're saying, well, if we don't have access to those, is there some workaround? And the workaround is to actually build an estimator. And this is getting us towards something called a Kalman filter. Have you ever heard of a Kalman filter? And if you haven't, then if somebody starts talking about a Kalman filter, you'll go, I've heard about that. I kind of understand what might be happening. We won't talk about a Kalman filter, thumbs up, but it will get us there, or start to get us in that direction. So when I was your age, well, I won't tell stories. The other idea that we will look at in pictures, again, we're looking at the picture book tonight. Don't want to go too deep and heavy, but maybe it will start to look a little that way, but just keep in mind the picture or the diagrams. We'll look at, now that we've built this estimator that now is estimating all state variables, all 10 components of our state vector, maybe from just one measurement, we've now been able to estimate all of these state variables. We'll use that instead of the state vector, because we don't have access to the state vector. We'll feed back those estimated states. And that's the last bulleted item in blue underneath our pictures or underneath our block diagrams. With respect to integral control, we will derive the augmented system matrices. And that concept of augmenting some dynamics with others is a very powerful concept. And I think if you can understand it for the integral control, it will make sense in other scenarios. Once we've built this system, and we'll build it directly from the block diagram, that's the importance of the block diagram, we'll discuss how do we identify the integrator gain and how do we pull off the state vector feedback gain from the augmented set of matrices. Augmented just means we're adding on to the original description dynamics, and we're building up our system matrix, our input matrix. All of those are being increased in size, in their dimensions. And we're going until 11:55 so that you have 4 minutes to complete your TCE if you haven't completed your TCE. That's why we are continuing to go this list of goals. The next thing that we will talk about is building this estimator. And once we've developed those equations, we'll say, well, how do we establish the estimator dynamics? Not only will we have closed loop dynamics for our system, but now we have to have dynamics of our estimator. How quickly are we converging to the true state variables with our estimated state variables? And we actually want to do that quicker than our system dynamics. Meaning, if we're applying an estimated position value as if it were the actual position value, and it's having a hard time keeping up with the actual position, we're out of luck. So we want our estimated values to converge quickly to where we want them to be, and then it makes sense to use those as if they are the actual variables. That's the idea. Whoa, we just keep going. Then we talk about using the full state feedback gain matrix that we've learned how to design with the estimated states. And putting all of that together now gives us a way to sort of design controllers by simply turning the crank. We don't have to scratch our head and go, I don't know where to put that pole and where to put that zero with this root locus. It's not working for me. In the state space approach, we can simply sort of pick some closed loop pole locations, find our K, then we'll go up in the alphabet and find an L for our estimator gain, and we'll put all of that together and we'll have a compensator that will work. And maybe that will give us some ideas or hints as to how we might go back and build a generic or general controller in the Z-plane approach that might be of lower dimension than this estimator based. Final exam info. I said I'll quickly go through this. It's comprehensive. There will be 15 questions. They will be distributed across the entire semester. But since the last material is sort of cumulative, I could give you one problem that has several problem parts, and it might reduce my grading. Meaning if you don't even know how to start, there's 5 questions that I don't have to grade. No. But the later material does depend on earlier material, and in that sense it might look like it's weighted towards the end material, but it's because you have all this foundational material from before that you're having to use. But the idea is that it will be distributed across the entire semester, and I've put together a topic list for the final exam, but that only includes material since exam number 3. So you now need to go back and look at exam topics 1, 2, and 3 and include that with exam topics for the final. Is that clear? The list that I am giving you for the final exam topics is not very long, but that's because it only includes the material since exam 3. I'm assuming you can go back and get the earlier topic lists for 1, 2, and 3. And I think all the other stuff is consistent with the previous exam, except now you get one more sheet of notes. So now you have 8 pages effectively, front and back, maybe 10 if you bring a 2-page transform packet from the web, and then you're going to have, wow, you might bring a suitcase full of your compass, your protractor, your ruler. I guess if you want to bring your slide rule, you may not need your graphing calculator. Some of you don't even know what a slide rule is, probably. That's okay. That's old school. All right, let's start looking at pictures. State space representation. We have several of these pictures, but I hope that this is now burned in your memory. That D is a delay, and it's a bank of delays, and how big that delay bank is depends on the dimension of your state vector x, or how big your system matrix is phi. If you have 10 state components in your x vector, then you have a bank of 10 delays in that one little box. So we're collapsing a lot of this information. There's a lot of signals in this one line for x of n if your state vector is 10 components tall. Is that clear? But this is now the picture, and you should be able to, from this picture, write down this set of dynamic equations and the output equation, and you should be able to go from this state space representation into a block diagram by simply connecting up summing junctions, matrix blocks for gains, and the delay block that processes or delays each of those state vector components. That's the state space representation. And this should just be review. You can now z-transform the state space. If you're looking to find the transfer function, you don't need to worry about initial conditions. And you can find now the transfer function g of z from that set of difference equations represented by your state space representation. Full state feedback. I basically just copied the state space representation from before, but now hopefully you can see in red what is happening when we apply state feedback. When we apply just state feedback, now we are not worried about injecting a reference signal. And what does this do for us? What kind of a system do we worry about if we're applying full state feedback without a reference input signal? What are we doing in a real world setting? Pardon? Yes, this is a regulator. We're really only worried about damping out initial conditions or disturbances in our state vector. We're not really saying we're interested in commanding our output to go somewhere. We're probably trying to regulate that y to 0. It's a regulation problem, and we're able to regulate it by shaping the dynamics. And when I say shaping the dynamics, you should be thinking closed loop what? Closed loop eigenvalues of your closed loop system matrix, which is phi sub c. And if some of you came up after class, what's today? Wednesday? Monday? And they were saying, didn't you forget some c subscripts? And I did. So in the video, they're not there, but I think after class I added those in at the latter part of that discussion. I was just getting quick and writing phi, but it really should have been capital Phi sub c, which was the closed loop system matrix, which in this case is phi minus gamma k. That's the closed loop system matrix, if you combine all of those together. I just started coloring today. So we have red for the full state feedback, and now we're implementing or adding on to that a non-zero reference signal. Now we can command that output y to go to a particular position. And on homework number 8, you are concerned with adjusting this N1 for what reason? Why would you want to modify or select N sub 1? You're interested in the DC gain. You want the DC gain between this reference R and this output Y. Typically, you would like that to be 1. So that if you inject a reference signal of 1 meter, your output goes to 1 meter. It doesn't go to 25 meters. You've adjusted this N1 to make that adjustment happen automatically. Last time we talked about that being very sensitive in terms of if we don't know all the entries in our system matrix accurately, then we're going to have some errors. And that's why we might like to have, I guess here I have some more analysis. But this is now the state space representation with full state feedback and a non-zero reference input. We're simply substituting u of n, or replacing u of n, with the structure minus kx plus n sub 1r. What is the dimension or dimensions of k? Is it clear from this discussion what the dimensions of k would be? How big is K? K, well, she's about this time. No, the matrix K. Pardon? 1 by 2. If I had given you anything, I didn't even tell you the system, did I? So you're sitting here going, what? I mean, if you go back to yesterday's class when we had a second order system, then you would know that you have two state variable components. And if we assume, or if we're told that the input, we only have one input, that's going to tell us what K is dimensionally. K, again, is trying to transfer the state vector into the input. It's linearly combining our state vector. So if it's TWO if we have two state components in our x of n vector, position and velocity, then and we only have one input, then K is going to be a 1 by 2 matrix, a row vector. What's n sub 1 if we have one input? It's a matrix, but it could be a 1 by 1 matrix, which is, you think of that as a scalar. And that's typically what we will be using in this class. Now applying that U of n, you could also find the dimension of K by saying, wait a minute, gamma K, that product better be compatible dimensionally with phi. And phi was our system matrix, that's 2 by 2. And if gamma was 2 by 1, then we need to multiply gamma by a 1 by 2 to expand that product to be a 2 by 2 matrix so that it's compatible with phi. Another way of thinking about phi. And we could call that phi sub c, and this is what you're using in homework number 1 or number 8, is you're looking at this transfer function t sub c of z and adjusting n sub 1 to typically create a DC gain between the reference input and the output of 1. And if we have a single input, single output system, that H, we're replacing Z with 1 because we're interested in the DC behavior. I minus phi sub c inverse, gamma, that's simply going to all collapse down into one number, a scalar, a 1 by 1 matrix, and that we can divide underneath. We don't have to worry about matrix inversion for a single input, single output. Questions on this? This is full state feedback with a non-zero reference input. And why do we want to use this? What did we learn about full state? Does it have any beneficial properties versus what we have been talking about or using before? Let's say transform-based controllers. What do we call those? C of Z's? Does this give us anything different than the transform-based control approach to use full state feedback? Pardon? So now we could end up with no errors if everything was accurately modeled and known. And it also gives us maybe more freedom to adjust the closed loop dynamics. But we're paying a price. The price is we're saying that we have to have sensors for every one of those state variable components. If my state vector is 5 tall, meaning maybe one is a position, one's a velocity, one's a temperature, one's a pressure, and one's a, what have I not used? Voltage. Yeah, we're in ECE. I forgot my voltage. And a voltage Then we have to have a voltage sensor, we have to have a temperature sensor, we have to have a position sensor, a velocity sensor, all of those in order to have access to each of those 5 variables. Then we scale those measured quantities and feed those back to form our input U. That's what's happening with full state feedback. The price we're paying is having to measure each of those state variable component signals and adjust those independently or individually and feed those back. Uh-oh. Wow. All right. Bear with me. Let's see if I can. Now we're adding integral control because maybe we don't know all of the elements in phi accurately enough. Maybe we don't know the elements in gamma accurately enough. Gamma is how we inject information into our system. And we liked integral control because that allowed us to drive our error to 0 if the whole system is stable. If we can guarantee that the whole system is stable, then that error signal is going to be driven to 0, and we will allow, if this is 0, if our error signal is 0, what does that tell us about our output? Pardon? It matches the input, doesn't it? And notice how I've labeled this. Maybe that's a little different than what we have, but I needed to do that because I'm introducing a negative sign inside here to be consistent with the negative here in the full state feedback, and so I didn't want to have a double negative on my output as it's coming through the system. This is simply an integrator block, this 1 over z minus 1. K sub I, the I is for integral, that's our integrator gain. And that's just a scalar. K is whatever dimension it needs to be to manipulate the state vector into the output, or I'm sorry, into the input. And this is now our block diagram for integral control with full state feedback. And what we are wanting to do then is figure out how to use this equation, this input equation, together with this set of dynamics and this set of dynamics. This tells us we have some new dynamics that we've introduced to help us drive errors to 0. And we can do that without having exact knowledge of phi and gamma and h. That's the idea. Whoa. Now, I told you this was a lot of pictures. Here is our full order estimator. So I'll cover up the bottom. Oh, that doesn't work, does it? So if I cover up the bottom, the top should look like the original system. But now what I'm assuming is I cannot go in and measure x of n. So now I want to build up a way of estimating x of n. Well, why don't I just copy what I know? And that's what I've done down below. I've just reintroduced exactly the same system in a model, and now I have maybe that lower one in my computer. The one up above is it's the airplane, or it's the vehicle, or it's the circuit. We don't have access to that, but we've modeled it, and now we're modeling it as the bottom. But we have to introduce some new things. If I now said, if I inject the same input into the top and the bottom, is y going to be the same coming out of both? Is y going to look the same if I apply the same input to both of these systems? The top one is our true system. This one is our model of that, and I'm going to assume that we know exactly the phi's are exactly the same, the gammas are exactly the same, and the h's are exactly the same. Are the y's the same coming out? Should be, huh? But I didn't tell you everything, did I? We maybe don't know the initial conditions. Darn it. Maybe this one up here has some offsets in its position, velocity, or voltage in its state vectors. And now if we drive those, this y may not look the same as the upper y because of this initial condition mismatch. And because of that, I can't label these down below as what they are up above. I have to basically say these are now estimated quantities. And since we're getting near the end of the semester, I'll just put a party hat on those vectors. Okay? If you're graduating, congratulations. You get 2 party hats. Maybe. We don't need 2 today. We'll distribute those across the different state vectors. Each one will just get 1. So now we have an x hat. That's the estimate of x. And we have a y hat. That's the estimate of y. And what we're assuming is we can only inject information into the system via the input u, and we can only measure y. We can't go up and access x. Maybe we can only measure the position of this system's displacement variable. And we can't measure velocity, we can't measure temperature, we can't measure pressure. All we can measure is the displacement. And that's our y. That's all we have access to. But we want to hopefully use that information on y to somehow make x hat move towards x. We want to drive the estimated state vector towards the actual state vector. And if all we can measure is y, well, why don't we take that y, and what color do I want to use? I don't know. Why don't we measure that y and compare it with what we're producing in our computer or in our model, y hat, and so we need to compare those. Let's just say that one's plus and that one's minus, and that now generates an error signal on the output. We'll just call that E sub y of n. So now we have an error signal between the true output and the estimated output, and we're going to try to use that to help us drive x hat towards x. Use the same. We're applying the same input to both the true system up above and the estimated system down below. We'll take this error signal, this output error, we'll process that through another gain matrix, L sub p, for a predicted estimator gain, and we'll allow that to adjust the dynamics driving the rate of change of our estimated state vector. And if we get a chance, we will derive the conditions on how L sub p fits into this, and this will be the dual problem to our full state feedback problem. This will be a full order estimator problem. And we'll use L sub p to move the estimator dynamics somewhere inside the unit circle so that they're much faster than our full state feedback dynamics, so that they're catching up to the position and they're not trailing behind the position and the velocity, that x hat goes towards x rather quickly, and then we can use x hat. What we'll do is we'll come down here and measure x hat in. We have access to that. That's in our system. And we'll gain that through k, and that will now feed our input u. And that's the next block diagram. But this is just the estimator. If you wanted to build something, let's say this is a capstone problem. Ooh, that's a bad word at this point, isn't it? Probably. This is now your senior design, and somebody gives you the task of identifying or estimating all of these variables in real time. And you say, oh, I can just build a full order estimator. And now my X hat is going to tell me what's going on inside that, let's say, motor. Now I can tell you what's happening inside the different pieces of that motor, possibly, if that was your system. And the way that you're doing that is you're injecting the same input to both, but you're comparing the true output, the physical system's output y, with your estimated output y hat. If they're different, that will create an error, and you'll use that error to adjust the x hat dynamics so that x hat goes to x. We've talked about a system being controllable. This one would need to be observable. It's a dual concept, meaning you need to be able to see all of your state vectors components through the output y. And then you can use L sub p to adjust the dynamics at will. That's the idea. Here's the same thing as before, almost. Now we're going to simply, I need to put some party hats on these, don't I? Because we know these aren't the same. Whoops. Even though our phis and h's and gammas may be identical, they may not be the same because maybe our system actually started at a different location than our than our estimated version did. We'll use that error signal but now to control this, now what we're going to do is we're going to measure, or we'll have access to x hat. We'll scale that with our full state feedback gain matrix that we've been using all along, and that will now drive not only our estimator but also our true system. And the combination will control this true system in a way that we want it to behave. That's the idea. All right. Now, let's quit looking at the picture book. Whoops, went the wrong direction. And let's talk about integral control. Maybe I didn't go the wrong direction. Here's integral control. Not quite, is it? Right now I have just the original system dynamics, and we want to introduce an integrator into this. And an integrator is trying to integrate away the error between our output signal y and our reference signal r. So that now, and maybe I don't really like this because I'm going to be mixing time domain and frequency domain, so I'm going to get rid of the time domain arguments here. And say that this is now z times x, and this is x. Let's say this is y and u, but in the transform domain, because I want to talk about, and this d I want that to be a bank of delays in the transform domain, because I want to build up my integrator in the frequency domain, or in the z domain. 1 over z minus 1 is an integrator. That's going to be my u. I knew I was running out of space. So I'm going to have to squeeze something in here. There's our u. That's supposed to be a summing junction, and what we are going to do now is we're now back to assuming we have access to the full state. We're going to scale that, and this may not be the same k, so I'm going to give it a party hat like before. This will now go here, but that's not going to give us all that we wanted, because maybe we do have inaccuracies in what phi actually is, or what gamma actually is. And for that reason, what we're wanting to do is we want to now compare the reference signal with a negative sign with our output with a positive sign. This is our integral gain, and this is our integrator block. And this is our full state feedback gain matrix. What we want to do is figure out how do we model this, and if we can model it, can we somehow create a strategy for figuring out how we can pick k hat and k sub I. But is this block diagram okay? Do you see, or do you have a feel for what's going on here? That's what I hope you're starting to do in this class. At this point in the class, I hope the black block diagram just screams at you, oh, that's just my state space representation, my dynamics, and my output equation. Yes?
So if your integral gain was not 1, would you need to scale your output from that gain as 1 over your integral gain?
So your integral gain, the integral gain, k sub I, we don't know what that's going to be. But we are making our output path be unity, meaning we're comparing the output y to the reference r. We're not scaling the output y when we're comparing it to our reference. So that what we really want to do is we would ideally like to see that that error signal is being driven to 0. We want to drive that error signal to 0, and by doing that, you can, if you think about this, if you have an integrator, and it's been integrating away, and it's generating some value, numerical value, what happens if you quit putting area underneath the curve in your integral? What's the output of that integral going to do? If you were summing and summing and summing, and you were generating numbers, and then you quit giving the integrator anything to sum, what's going to happen to the output of the integrator? It's going to stay at whatever it was that it had for a value, wasn't it? It's not going to go to 0. It's going to, even though the input to that might be 0, it's going to be injecting information out because it's built up that information over time. Is that making sense? so that even though the error is going to 0, you may still be applying some non-zero information into your system through U. That's the beauty of the integrator. What we want to do now is take this from the picture, from the block diagram, into some equations so that you can now manipulate those to design for k hat and k sub I, so that you can compute these. Right now we don't know what those are, but let's figure out a way to model this, and then we'll be able to see how do we find k hat and k sub I. Just like you could find k. Does everyone know how to find k on the final? If I gave you a full state feedback problem and said, I want your closed loop poles or your closed loop eigenvalues to be at these locations, can you all find the full state feedback gain matrix K? That you need to be able to do. We want to now translate this problem, which now has this stuff added, into an equivalent problem. And then you'll be able to do that. So let's see if we can do that. What we want to do now is, let's just say that we are going to do an implementation or implementing this integral control structure. Or another way of finding that is we're finding Elmo. Oh, I'm not Elmo. Who do you find? Waldo. Finding Waldo. Who's Elmo? Nemo, wasn't it? I don't know. I don't go to movies. I don't watch movies, obviously. So now it's finding Waldo, or where's Waldo? It's finding Nemo, isn't it? All right. Where's Waldo? I don't know where Waldo is. We don't need to worry about Waldo. We need to find k sub I and k hat. That's what I want to be able to do. If that's the case, let's start with trying to figure out what's going on here. Or maybe even before that, let's say that this signal right here, let's call this x sub I. So x sub I is the state vector component that's the output of that integrator block, and the input to that integrator block is E. And this is just a final exam review problem, as easy as it gets, really. So let's now look at the dynamics of what we've just drawn via a block diagram. So this is prime material for sketching on napkins. If you're now in an interview and somebody says, oh, what did you do in class tonight? You can say, well, I was designing integral controllers. Can you explain that to me? Sure, where's a napkin? So you pull out a napkin and you start writing down the dynamics of this, and you impress your interviewer. Let's look at the dynamics, and in particular, the integral term. And the reason this is nice is because it helps you review for the final exam, which is Friday. That's our commercial. The exam is Friday at 6, right? So if you come here 48 hours from now, you're going to miss 20 minutes of your exam. Don't do that, because it's a long exam. So get plenty of rest between now and then, but not so much that you sleep through the final. 1 over z minus 1, that's the block, that's the integrator block. Here's the output, x sub I, and here's the input, E. Now if I said derive the difference equation associated with that, you better be able to do it on the exam, right? Probably won't get any easier than this on the final. So you get that picture and you say, oh, that's x sub I in the z domain. That's the output, and that's equal to 1 over z minus 1 times e of z. See, this is so easy, you're yawning. Or I start talking about sleep, and I've lost half of my audience. I'd already lost the first half. Now I'm all alone. I can do whatever I want, can't I? You guys won't be any wiser, especially those at home. Now what do? I want a difference equation because I want to introduce, I need to augment my earlier dynamics, which are x of n plus 1 equal phi x of n plus gamma u of n. I want to augment that with what this produces. So what's the difference equation look like for this? Well, let me just cross multiply, and I have z minus 1 x sub I of z is equal to e of z. That should be straightforward. Now I have z x sub I of z minus x sub I of z equaling e of z. Shouldn't be any questions with that. Are there any questions with that? That should be clear. You should be comfortable with that. If you're not, please get comfortable with that because it's not going to get any easier than that for the final. Okay? Now, if we go into the time domain, and I isolate my most or my highest indexed x sub I value on the left and put everything else on the right, are we okay with that expression? And that's just an integrator, isn't it? Whatever we had in the variable x sub I of n, we add the error signal to that. And this just sums it up. That's what an integrator is doing. And somebody might say, oh, if you have a forgetful integrator, they might have put some scaling in here and made it 0.95. And then it's sort of forgetting. It's getting old. It's forgetting what it had in the last time step to get you to the next time step. But here we have a pure integrator. It remembers what it had in the last time interval. It adds the error, and now we're just building up whatever that error signal is producing in our integrator. But what's E? What was E in our block diagram? Again, we're just going from pictures, our napkin. E is made up of the reference with a minus sign on the reference and the output Y with a plus sign. That's how we defined E in this block diagram. Different maybe than what we've done in the past. So from the block diagram, E of n was actually Y of n minus R of n. But what's Y of n in terms of state vectors, or in terms of the state vector? Again, if we go back here, Y is just the state vector scaled by H. H is somehow sort of measuring all the state vectors and combining those into one number if we have one output into our output Y. So that Y is actually hx of n minus r of n. And if we put that error into the integrator formula, then we have x sub I of n plus 1 is equal to x sub I of n plus h x of n minus r of n. Questions on that? This is now the dynamic behavior that we need to augment on top of or onto the earlier dynamics from our system, x of n plus 1, how it behaves. And this is just an integrator. And it's integrating the error signal, but now we've described the error signal in terms of our state vector and the reference input R. Let's now increase our matrices. Let's now augment the integral dynamics, which is what I've just highlighted in the rectangular box. Let's augment the integral dynamics onto the original dynamics. By that, I simply mean I'm stacking another state vector component onto the original state vector. If I had 10 components in X, now I'm just going to put X sub I on the top of it. And now my state vector, my augmented state vector, is 11 tall. Is that clear? I'm now going to have X sub I, maybe I shouldn't make that disappear. I have X sub I of n plus 1 is equal to X sub I of n plus hx of n minus r of n, and I have x of n plus 1 equaling phi x of n plus gamma u of n. And I apologize, somebody came up after Monday's class and was commenting on my penmanship, or the lack thereof, and they said, your gamma looks like your R. And I thought, ooh, really? So it kind of does, but I hope you know what is what, okay? I'm not offended by that. I didn't understand the question for the longest time, but then I got it. So if the gamma, that's a Greek letter, and this is a English R. They're completely different. Okay? So please, I hope that doesn't confuse you. Now, what do we do? Well, let's now build this into a matrix representation. We just said that we are going to make x sub I n plus 1 stacked on top of x. And x sub I is 1 in height. X, we haven't said. It might be 10 tall. It might be 4 tall. It might be 2 tall. Maybe it's a 1 by 1. Maybe this augmented vector is just a 2 by 1 vector. But now what we want to do is write that in terms of x sub I of n and x of n plus something. Uh-oh, I'm going to have to tape some more pages on, or width on, but that's easy for me to do. Plus, that's R. Gosh, now that that was pointed out to me, it does look like a gamma. But that's supposed to be a little lowercase r. Is that clear? So now I need to make all of that, or the top two equations, fit into these augmented dynamics. Is it clear what's happening? If x, let's just say x is 10 tall, then how big is this empty system matrix? And let's say I only have the one integrator. How big is that empty system matrix dimensionally? The lower right-hand corner, this is a block matrix structure. If you can't see it, it's right there, meaning this has to be block matrix compatible with the left-hand side and the right-hand side. And x sub I is 1 tall, x is 10 tall. So this is 1 and 10 below it. So that state vector now augmented is 11 tall. If our state vector is 11 tall, what's our system matrix? Has to be square, doesn't it? So it's 11 by 11. It's grown from 10 by 10 to 11 by 11 because we've added an integrator. I now need to make whatever is happening here, and this is now split into two pieces. It has to be partitioned compatibly with the left-hand side. That's an equality sign. So it has to be true. Whatever on the left has to equal what's on the right. Is that clear? Now what we want to do is in all of these spaces, these empties, we need to put in the appropriate expression to read or to duplicate those two equations up above. How do we build, let's work at the bottom first. How do we build x of n plus 1? We just look at the second equation, don't we? And we say, oh, that must be phi x of n. Where do I put phi? In the lower right, because I shouldn't be adding x sub I into x directly, should I? So this actually should be 0. And how big is that 0? What are the dimensions on that 0 in our hypothetical example? How tall is it? Is it short or is it tall? It's the same height as phi. How tall is phi? 10. How wide is that 0? It's 1 wide, isn't it? So that's now a vector that's 10 by 1. Is that clear? Even though you can't tell what it is necessarily. So now I have accounted for this piece. Is that clear? That's all I've done so far. Now I want to introduce gamma u. Where does that go? It's going into the matrix preceding the u, isn't it? Right there. Does the reference signal directly influence the dynamics of x of n plus 1? No, so I need to put a 0 there. And how big is that 0? 10 by 1 again, isn't it? Has to be one column because I only have the one reference, and it has to be as tall as the state vector x, which was 10 tall. So that 0, although it looks like a 0, it's a matrix that's 10 by 1. Is that clear? And now we've completed the second equation. We've now produced x of n plus 1. That's what we started with. Now we need to augment those dynamics with our integrator dynamics. So now in this top block row, we need x sub I of n plus 1 to be what's upstairs, or in the first equation. Any idea? This is just a 1, isn't it? Because we need x sub I of n plus 1 to be x sub I. And x sub I was 1 by 1. And this little block right here, the upper left-hand block, is a 1 by 1 submatrix, which is just a scalar 1. Is that clear? Anything non-zero in the 1, 2 submatrix? H. We need to pull up, or we need to weight x with h. So we've accounted for that and that. Does u explicitly come into our integrator dynamics? How big is that 0? Well, this one was 10 by 1. This one was 10 by 1. So those zeros, they may look the same, but they're not the same. That last zero I just put up there is a 1 by 1. Is that okay? Is anything in the top submatrix of the matrix that's pre-multiplying the reference signal R? That's a -1. Is everybody clear on how we've built this augmented set of dynamics? That's now our new, you could say that this is now a new system matrix. I'm partied out, so I'm just going to give it a flat hat. Okay? Phi bar. This is now gamma bar. And I haven't even decided to give this one a name, the second input vector or matrix. But now, if we can play with phi bar and gamma bar just like we played with phi and gamma before. It's just now they've grown a little bit. They're a little bigger, and they have specific structure to them. What's our control law look like? We want the control law to be in terms of our state vector, because we want to apply full state feedback again. So now the control law we can find directly from the block diagram. U of n, if we go up to our block diagram, do you see how beneficial this block diagram was? U of n, which is what this will be in the time domain, is just minus k sub I x sub I of n. That's one of our state vector components. Minus k hat x of n. That's U of n, directly from the block diagram. So now we know U of n is equal to minus, and we hatted this one. We were still in our party mode. This was minus k hat x of n. Why did I do that? Let me not do that, because I've done my integrator first. So what was the integrator? That was minus k sub I x sub I of n. Minus, now we're back to the party, k hat x of n. That's our U of n. But I hope it's clear that we could write that as a minus k sub I k hat times our new augmented state vector. And we could call this k bar. And now we're in our full state feedback design strategy. We now need to find or design our k bar. Once we've found k bar, we can partition that k bar. What's k sub I dimensionally if we have one input? How wide is k sub I? Just one, isn't it? So k sub I is a 1 by 1 scalar, and k hat is 1 tall, and it's as wide as our original state vector. It's maybe 10 wide. Here's the process. Now from the block diagram, we've extracted all the information we need in our equations, and now we can walk through the control law design when we're implementing integral control with full state feedback. So this is now how you can design an integral controller to enhance what you were getting with full state feedback. What we want to do is we want to place the poles of phi bar minus gamma bar k bar with the choice of k bar. And k bar is going to be for a single input. Oh, that's, see, now I'm overusing my n's. N is now the dimension of my state vector and not the time index n. Is that clear? N is 10 in our example. It's not the time index n in this situation. And this is for a single input, since we have ones floating around. Now, once we've, and is it clear how you build phi bar? You've created phi bar. You need the output matrix, the original system matrix phi, and a 1, and put those in the appropriate location. Now you have phi bar. Gamma, easy. 0 on top of gamma, the original input matrix. Now you have a system matrix and an input matrix. You know how to pick k bar. That's what everybody said 10 minutes ago. They can design full state feedback. Once you've found k bar, now you just need to divide it or split it up to identify the integrator gain and the full state feedback gain and put it into your block diagram, into your system. So this is really the design process. Place the poles of phi bar minus gamma bar k bar with k bar, and once you have k bar, once k bar is determined, to place the n plus 1 eigenvalues of phi bar minus gamma bar k bar the very first column in k bar equals what? K sub I. That's our integrator gain. That equals K sub I. And the last, or the remaining, n columns of K bar yield the new full state feedback matrix, which we were calling K hat, which was an element of 1 by n. Remember, K bar was just this K sub I. It was compatibly partitioned with our new state vector, X sub I and X. Is that clear? If I now give you this on the final, will I not have to grade too much? Yes. So now what we were wanting to do is we need to place the poles of phi bar minus gamma bar k bar. And we have to basically throw away our earlier full state feedback gain matrix because now we have a new problem. But we may know exactly where we want those poles to live. What we don't know is where we want our integrator dynamics to be moved into the unit circle. So we now have to add on one more closed loop pole from where we wanted in our, let's say, 10 by 10 original. Now we introduce another one, and we may make it about the same or maybe a little faster, not much faster. We won't want to really tax our system, but we make our additional closed loop pole in the same range as the fastest of our original closed loop poles. Now we have 11 closed loop poles that we will place with K bar. And this K hat may not be the same as what K was when we had the original 10 by 10. It's going to be different because we now have a different problem, phi bar minus gamma bar, that we're using to control the system. Other questions? Do you want a gift? This won't be on the final, but the reference input will. But I can't tell you that before. You won't pay attention. You're welcome. But I want you to understand how to do this. There were steps in there that were review for the final. How do we get difference equations from a transfer function description? And if you may have to do this when you get out or when you get to another course, and I want you to feel comfortable when people start augmenting dynamics all over the place, because that's really what you're doing when you're doing full state estimators. Now you're augmenting with an n by 1 and an n by 1. You now have doubled your state vector in the augmented dynamics. We won't pick up at that point because we do not have another lecture, but we do have a review session in a few minutes. Thank you, and I'll see you at the final, if not in a little bit.